The textbook defines a probability distribution as a list of outcomes of a random process where the outcomes are disjoint. The probability for each outcome is between 0 and 1, and all outcomes sum to 1. If you perform an experiment, it may only have two outcomes, like success, failure. It might have an infinite number of outcomes. Whatever the case, each outcome has a probability associated with it, even if that probability is 0. A probability distribution lays out the probabilities of all the events. Rolling a single die can be thought of as an experiment with 6 outcomes, and they're all equally likely. This is called a discrete uniform distribution. It's uniform in the sense that the events have a uniform probability of occurring. A discrete distribution is a distribution that has a countable number of events. I might post something on what countability means, but for this class, think of it as meaning that all outcomes can be converted to some list of integers or whole numbers, even if that number is infinite. Like the roll of a die can be listed 1, 2, 3, 4, 5, 6, or heads and tails can be listed 1, 0. Yes, no, maybe can be converted to 1, 2, 3, etc. Let big X be the random variable that represents the value of the die. Let little x be the realized value. Our notation will be px equals 1 when we mean the probability that the die roll equals 1, and px equals 2 for the probability that the value of the die is 2, and so on. This table here is listing two things. The probability that the die equals some number, which is the first row. This is called the probability mass function. In general, it refers to the probability that the random variable equals some number. And the second row is listing the cumulative distribution function. This is the probability that x is less than or equal to the number. For example, the probability that x is less than or equal to 3 is the probability that the die comes up 1, 2, or 3, which is 1/2. Today, we're learning about the normal distribution, which is a continuous probability distribution. A random variable that has a continuous distribution can take on any value in some range or collection of ranges. The number of outcomes is uncountable in the sense that we can't keep track of how many there are. For example, let's say I randomly draw a point from the interval 0, 2. So here's the interval 0 to 2. And let's say that all points are equally likely. This is called a continuous uniform distribution. If x is the point I get, x might be 1.2, it might be 0.3334, it could be 1.78215647, and on and on and on forever. It could be anything in this interval. There's no way to keep track of all the outcomes. That's why the number of outcomes is said to be uncountable. For a continuous random variable, we have a probability density function, or PDF, instead of a probability mass function, or PMF, like we had with discrete variables. Because there are so many options for x to be, the probability that x equals any particular value is taken to be 0. So px equals little x equals 0 for any random variable x that follows a continuous distribution. The PDF specifies the height of a density curve, and you'll see why I call it a curve in a minute, but here it's going to be more of a rectangle shape. When we're dealing with continuous variables, we use this PDF function to draw a graph that has area 1. Then probabilities can be found based on how much area they take up. In this case, all values are equally likely, so the PDF is f of x equals 1/2. F of x gives me the height of a rectangle, and the width is 2 because the possible values for x range from 0 to 2. To make this thing a probability distribution, I need the area to be 1. That's why f of x needs to be 1/2, because the area of a rectangle is base times height. Now, like I said, the probability that x equals some number is 0. But we can still find the probability that x is in some range by comparing the area of the range to the whole. For this distribution, the probability that x is less than or equal to 0.6 is the area of the rectangle behind 0.6. We have a rectangle with base 0.6 and height 1/2. Base times height is 0.6 times 1/2, which is 0.3. So the probability of drawing a number less than or equal to 0.6 in this situation is 0.3. This is the cumulative distribution function from before. The probability that x is less than or equal to some number. Continuous distributions and discrete distributions both have a CDF, but a continuous distribution has a PDF, and a discrete distribution has a PMF. Remember that for continuous distributions, the probability that x equals something is 0. So the probability that x is less than or equal to little x is the same as the probability that x is strictly less than little x. The same applies to the other direction as well. This is only for continuous distributions, remember. If you roll a die, the probability that your roll is less than 2 is 1/6. But the probability that it's less than or equal to 2 is 1/3. This doesn't work for discrete distributions.